Okay, today we're gonna talk about so-called nonlinear instability. It's a very interesting phenomenon that if you're not careless, if you're not careful, that phenomenon can destroy your numerical solution, and it sometimes seems coming from nowhere. And so we talk about nonlinear instability. So far, when we considered approximations of finite difference approximation to our differential equations, we assume that our differential equations are linear. So we considered equations like, for example, in our field, say du dt plus some translation velocity c du dx. So this advection equals, say, some diffusion so this is kind of typical equation where we assume that c is some constant and nu is constant, and then we used we approximated derivatives with some finite difference form, and then used von Neumann a method to show stability of that particular finite difference representation of this differential equation. And of course it all only works if those coefficients are not functions of, say, u itself. So those are, in this case, they are linear. In reality, of course, we have, so this is linear equation, and this is actual one. So it may look something like that. So for momentum equation, u is velocity. So u is advected by itself, by velocity itself, and it's say equals to nu, which can be function of x and time itself, and velocity too, for example, I don't know, in general form, if it's some subgrid scale parameterization. So it's a nu, which is can be function of x, time, and actually of u, du dx. And when we talk about subgrid scale parameterization, we actually will talk how to find this so-called ADA diffusivity. So you see that in that case, this is nonlinear term. And generally, we can't use von Neumann stability method in this case, because for von Neumann to work, we want to our solution to be superposition of harmonics, Fourier harmonics, and those harmonics don't interact with each other. So we can consider stability of one particular harmonic, and then show that all those harmonics are stable, or all of them should be, if just part of them are stable, those that remain may be unstable, and then if even single harmonic is unstable, then the whole solution is unstable. So then we derive this criteria. For example, for advection, we derive that like mu equal to c delta t divided by delta x should be smaller than some mu naught, which is can be 1, can be 2, can be half, depending on the particular finite difference scheme you use. In case, so this criterion we derive for this linear equation, and we still apply it for nonlinear equation, but we just assume that instead of this condition, we would use that max of absolute value of u for all k. So maximum on a grid times delta t divided by delta x should be smaller or equal than our linear stability criterion. So this is what we would apply in an actual situation for our actual finite difference scheme. And similar for diffusion. We find some maximum nu, and based on that we apply our criterion for stability of diffusion equation that we derive using linear diffusion equation. So that's nice and very straightforward. Unfortunately, as was discovered a long time ago by a meteorologist, modeler, one of the first modelers in our field, by name Norm Phillips. In 1959. So Norm Phillips was one of the first modelers or numerical meteorologists who actually created one of the first weather forecasting model using some barotrophic or quasi-geostrophic equations, two-dimensional, two-level quasi-geostrophic model. And so in 57, he actually made some simulation and found that while simulation progressed finally for 2 weeks, of real time of integration, at the end of about 2 weeks, all of a sudden it just exploded. It became unstable, even though all this time this kind of criteria that they used was just so this criterion was actually satisfied the whole time. This linear stability criterion was satisfied on the grid, but the model still became unstable and blew up. So he started analyzing what's going on, and he realized that the term which was responsible for this behavior, this nonlinear term, and this instability, even that occurs even if you have linear stability criterion satisfied, this instability is just since then is called nonlinear instability. So let's discuss where this instability actually comes from. So when you look at nonlinear equations, what they actually create, what's the problem with them? The problem with them that if you feed them some Fourier harmonics, they actually produce new Fourier harmonics as a result. So, for example, and linear equations don't, of course, produce new Fourier harmonics. If you feed them only, say, harmonics or with certain wavelengths. So for linear equation, so if you have initially some Fourier sinus harmonic like that, so wavelength is lambda. So as time goes, time of integration, then it still will be harmonic with wavelength lambda, and maybe amplitude will change. So amplitude change, but not wave number or wavelength. Or k, or wave number k. So that's what's happening in linear equations. In nonlinear, you create new harmonics. So For example, let's consider this term u du dx, and we consider harmonic, Fourier harmonic, sum u tilde amplitude times e to the power of I kx. So this is our kind of complex representation of a wave. So now let's substitute in here. What we get here, we have u tilde squared. It's not function of x. And then you have e I kx from this guy. And this guy you differentiate, you get I k and then e to the power of I kx. So now what you have, harmonic times ik e to the power of I 2kx. So now you see that we had originally harmonic of wave number k, and after this interaction, after this term, what you created is a harmonic 2k. And 2k means it's what? K is 2 pi divided by lambda, where lambda is wavelength. So you see that 2k means that you created q star equals 2 pi over lambda star. So lambda star, new wave, became lambda divided by 2. So you created wave with half wavelength than the original one. And that all comes from this nonlinear term. So we only consider this this particular one harmonic, but let's say that there are many of them simultaneously. So this term, let's say that you have u, which is a superposition of all these harmonics. So such that you have this many harmonics like that, where this k can be like 1, 2, 3, 4, 5, and so on. So now if you consider this u, say du dx, you actually have u, which is harmonics, say, let's consider pair of harmonics, k and m. So u will be k, and here u is going to be m. Then you have u k times u m. Now uk is e to the power of I kx, and then this one is going to be I mx. You differentiate, it's I m e I mx. So now you produce harmonic which has amplitude k u m I m, and then I k plus m. So you see you get now if you have many harmonics, and the actual solution is just basically many harmonics, and you subject them to these terms, then two of them with wave number k and another one with wave number m will create some harmonic k plus m. And because we have complex conjugate of those numbers, remember that complex conjugate, this one is if this is a complex number, ikx, this is our wave, then the complex conjugate is I minus ikm. So what's conjugate? It's the same wave that has the same amplitude, the same wavelength, but its phase is different. It's shifted. So phase is basically position along the x-axis, and So basically, if it's shifted a little bit, then, well, by certain amount, you have this conjugate. So actually, if you have conjugate, then if you multiply two waves, so you have a nonlinear term like u times v, and here you have I, k, x, and here you have I, m, x, but here is plus minus because it can be just shifted in phase. So you have two different ways. You get some k plus minus m waves. So it can be when you have interaction of two waves with wave number k and wave number m, you can produce nonlinear interaction. You can produce waves when with wave number k plus m or k minus m. Well, so for example, so what's if those k m on a grid is basically related to wave number, and so what are the shortest waves that can be represented on a grid? We talked about that some time ago. So shortest waves on a grid, say with constant delta x. So we have times grid spacing constant. Then of course shortest waves are lambda, let's call it lambda mean equals to, of course, 2 delta x. So 2 grid spacing. So that's the shortest ways that can be represented, which correspond that k max, because wave number is inversely proportional to lambda. So smallest lambda means biggest k, or wave number that can be represented on the grid. So it's 2 pi divided by lambda, which is 2 delta x. So shortest waves are pi divided by delta x. This is the shortest wave number. So so now let's imagine that we have this. So other wave numbers, what are those? So we have so this is our k, and this one is k equal to 0, which means just mean, the grid mean. No, it's not even wave. 1, it means harmonic number 1, it's one sine wave through the whole domain, right? And 2 and 3 and so on. 3 means 3 sines, full sines over the width of your domain, and so on. And let's say that our grid can represent only only can represent 4 such waves. I mean, let's say 6. Let's make it longer. So this is in reality. In reality, it can be infinite. So this k here is infinite. So in reality, you have continuous space, and you can have waves as short as you want. But in reality, you have this. This is the shortest one. So in this case, this is wave number 6 that correspond to, say, to 2 delta x waves. So now if you have interaction between, say, wave 3 and 4, nonlinear interaction. So wave numbers are added and subtracted. So interaction of these two guys, what creates? 3 and 4, if they subtracted, it's 4 minus 3 is 1. So they may create this wave. So you see, two short waves can create a longer wave. They cannot create negative one because negative one is basically the same as one, it just phase is different. So all these interactions, say wave 1 and 2 produces again one wave. And wave 2 and 3, if you subtract 2 from 3, it's 1, so it creates this wave. So when they subtracted, they create this kind of longer waves. But if they add it, they create shorter waves. And in this case, 3 plus 4, it should create this wave. With wave number 7, but there is no wave number 7. The shortest wave, the largest wave number we can get on this grid is 6. So do they just disappear? So in reality, in nature, it would create 7 and so on. And this was responsible for this cascade of energy to shortest wavelengths, like in turbulence. You have this big eddy and then it becomes smaller and smaller and smaller and smaller because there is this cascade. But in the model, you don't have that. You have this shortest waves that it can represent, and that will stop there. Does it mean that if those two waves interact, they create wave number 7, which cannot be represented on this? So this one cannot be represented. Does it mean that they just disappear? No, apparently it's not. And it is an interesting phenomenon. It's called wave aliasing. So what it means that some other wave is created that can be represented on this grid. So this is called wave aliasing. So let's consider that wave aliasing example. So let's say that we have some cosine function k with wavelength cosine kx. So now we have this k max on here, k max equals to pi divided by delta x. So that x equals to what? I delta x, not I, let's use m delta x, where m is 0, 1, 2, 3, some grid point indices. So, but this is our maximum k max. Maximum wave number that can be represented on this grid. So let's write the cosine just 2k max minus 2k max and plus k x. So we didn't change anything, we just added 2k max and subtracted 2k max. So we have cosine 2k max x minus 2k max minus k x. So 2k max x equals to 2k m delta x equals this max equals to 2 times pi divided by delta x m delta x cancels, so it's 2 pi times m. So this guy is just 2 pi times m, or just 2 pi, same as the integer number. So you know that if you add 2 pi to any angle for cosine, it's going to be the same cosine, right? You just make full circle. So you do it 5 times, it's still the same thing. So it's 2 pi minus 2k max minus kx, and this is the same thing, and cosine of minus or cosine of plus is the same thing. So 2 pi goes, you have 2k max minus kx. So these two guys are the same. So k can be actually be the same wave on that limited grid if you have wave number 2k max minus k. So it would behave the same as our original cosine function. So instead of, if you cannot represent wave number with wave number k, this is how it will be represented. So this one, kx, cannot be represented. Instead, this what cosine of this function will be presented. And it will have the same values in grid points as this one that is not represented, but this guy can be represented, and it will have the same values in grid points as this wave that cannot be represented with this k that cannot be represented on this grid. So so this is important formula that we'll use later. Let's write it here. This aliasing, that k, this earliest value, so this is earliest value equals to 2k max minus k. So this is earliest wave. Okay. So now let's consider two waves, k and m, that interacted and created new wave, which is k plus m. And such that, so let's consider, so let's have two waves, k and m, wave numbers k and m, such that k plus m, when they interact, they're actually greater than k max. So they cannot be represented on this grid. So let's write it. What it's going to alias to. So these waves interacted, and what wave will be created? Well, we'll see. So we have this k star. That's a wave that will be created, equals to 2k max minus k plus m. So this is wave number that cannot be represented, and this is wave number that it will be represented, like. So if you look at this, so let's see if this wave is indeed can be represented. Let's see. For that, we need to show that this k star is smaller than k max. So let's see. So k plus m is, in our case, it's greater than k max. But obviously, because each of k and m's are smaller than k max, it means that k plus m is smaller than 2k max. Okay, so so now let's change the sign here. Minus, 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 and if you multiply by -1, you remember that from algebra, you need to change the signs. I mean the equality signs, non-equality signs. So now we add 2k max here. We have 0 equals 2k max minus k plus m, and smaller than k max. We just added 2k max to everybody. So which means that this guy, 2k max minus this, so this is our k star, is actually smaller than k max. So indeed, our earliest wave that is created in response to the fact that two waves that are represented on the grid create some wave which cannot be represented, it actually produces this earliest wave number k star such that it's actually represented on the grid. So we demonstrated that. So in this, let's see what it means. Like in our example, so if you have basically our wave number of k, this is our final, so it's 6, 5, 4, 3, 2, 1, 0. So we have two waves interact, 3 and 4. So k equal to 3, m equal to 4, and our k star, I mean k max, is 6. So which wave we will create if we interact 3 and 4 is not 7. That cannot be. So instead what it will create is k star equals to 2 times k max, so 12, minus k minus 3 plus 4, or minus 7, equals to 5. So instead, interaction of wave 3 and 4 will create wave number 5. And remember, and again, this only happens because we cannot represent longer waves. In nature, wave number 7 would be created. But in model, wave number 5 would be created, just because we have limited grid, because we have limited representation of continuous space, and our space is discontinuous, it's discrete. This is purely that effect, because of that effect. So this aliasing is only because of grid. It has nothing to do with actual physical process. Okay, so now instability. Why we have nonlinear instability? So when we integrate the model and we have all this bunch of nonlinear terms, and we constantly create these new harmonics, new waves. So two shorter waves create longer wave, or two shorter waves create shorter wave, and some of those short waves cannot be represented, so they continuously aliasing to some waves that can be represented, and so generally, and then these new waves that appeared, they interact with other waves, they jump into turn into other waves with different wavelengths. So there is this kind of soup of like bubbling soup of waves that created, destroyed, added to each other, subtracted from each other. So there is this kind of this is what's called solution to differential equation. So all of a sudden something makes sense from all this. So we have cyclone, or some anticyclone, or some cloud developing. So all these waves, this is all interaction of those waves. But once in a while, you may, in order for instability to occur, you need to create certain waves faster than they're being destroyed. So if you have some certain waves that created, so you add energy to that wave number. And then other processes actually take that energy away and create some other waves. If they keep up, so in equilibrium, nothing really happens. There is some amplitude, average amplitude of those waves with certain amplitude, and everything is fine. So everything is stable. But as long as it's like with any explosion, if you create energy faster or put energy in certain scale, in this case in certain waves, faster than they being taken away by other processes, then it will start accumulating and eventually it goes out of control and the explosion happens. So are those waves? Actually, it turns out that there are those very dangerous waves that have a tendency to aliase, to do this aliasing right into themselves. So they're basically interacting with other waves, create themselves. So basically, instead of getting rid of energy, they tend to hold into that energy. And let's see what those waves are. So let's consider, because that's actually a recipe for disaster, right? If you have waves that interact with some other wave, and Alice wave is actually the same wave that to start with, to begin with, then you don't get rid of energy. And then if you keep adding energy from other waves, your energy will start building up. So let's find those waves that actually exist. So we have this aliasing formula, and so in this case, the waves that create themselves is waves that if you have k interact with some m, with some other k, to create k star. So we're looking for the process. K star equals to 2k max minus interacting with k star plus k. So some wave k, which is not k star, interacting with wave k star produce k star. In that case, you have explosion. You may have explosion because k star creates k star. Energy is not effectively vented out. It tends to, so this energy takes energy from wave number k and converts it back to, so this k star wave takes and interacts with wave k and creates itself, so adds more energy to it from this wave k. So you see it's kind of sucking all the energy from this wave k. So let's write it the following. We have 2k star equals to 2k max minus k, or k star equals to k max minus k over 2. So let's now find this combination of k star and k that makes this work. K star is some 2 pi divided by m delta x. So this wavelength m, that's what we're gonna find. And k max, this is maximum wave number represented on the grid. Remember, 2 delta x waves, so this is pi divided by delta x minus k, which is 2 pi and pi, 2 and divided by 2, so it's pi divided by some n delta x. Yeah, so from that we can easily derive that n should be equal to m divided by m minus 2, and n is an integer number, that's a certain wave. So n is an integer number, and there is only one possibility here, that m equals to 4, then n equals to 2. So this is what we found, that 4 delta x waves, so 4 delta x waves interact with 2 delta x waves to produce again 4 delta x waves. So basically, if you have energy in 4 delta x waves and 2 delta x waves, and then they interact, then 4 delta x basically sucking all the energy from 2 delta x and grow. And then some process create more 2 delta x waves, and they interact with 4 delta x waves, create even more energy in 4 delta x waves, and so on. So normally 4 delta x waves of course interact with other waves, and if this process of interaction with other waves is faster or the same as the process of amplifying 4 delta x through this process, then nothing will happen. It will be just some noise in the shortest wavelengths like 4 delta x and 2 delta x waves. But if it's managed like that, for example, you remove the energy by diffusion or something, then nothing will happen. But once in a while, if you don't have enough diffusion, not enough interaction with other waves to remove this energy from 4 delta x waves, then the energy will start growing unbound, and eventually it will destroy the solution. It will be instability, explosion. So this is the process that creates nonlinear instability. 4 delta x interacting with 2 delta x waves. So what's the remedies? What are the remedies to address this problem? How to make sure that your solution is not susceptible to this very nasty phenomenon? And believe me, it's pretty nasty. It just comes from nowhere. Your solution behaves fine, and then all of a sudden, somewhere in the domain, some explosion happens, and your solution is destroyed. So what's the remedies? Obviously, you need somehow to control 2 and 4 delta x waves. Try to make them their amplitudes smaller. So try to remove energy from them, for example. That's one of the remedies. So nonlinear instability, some remedies. So first, suppress. So suppress or filter 2 delta x and 4 delta x waves. And this is fine because those waves are short, the shortest that can be represented, and they don't really participate so much in solution because, well, in order to resolve something you need more waves than that, right? Longer waves. Remember, it's like you need at least like 10 delta x waves, but it doesn't mean that you completely remove them, because they're actually part of the solution, because like they produce some of the solution by themselves because they need it for Fourier decomposition of your solution. If you remove them entirely, then what grid are you running at? If you remove 2 and delta x waves, it means that effectively you're running on a grid which is 4 times coarser than your actual grid. So you're basically wasting all this computer time. So you should not remove them entirely, but you should remove them just enough to control nonlinear instability from happening, but at the same time not over smooth your solution, because if your solution like that, because it has 2 delta x and 4 delta x, maybe it's fine. And by removing them, you make your solution like that looks very smooth. But then it's over filter. So it's too smooth solution. And actually, indeed, if you look at some model outputs, I'm not going to name those models, but some of those models, if you look at them, you run them, say, at 1 kilometer grid spacing, and then you look at the solution. It looks like very smooth, all smooth, very smooth clouds, everything is kind of very smooth, and then you wonder why it's 1 kilometer. I don't see any 1 kilometer information there. It's all like looks like I don't know, like at least like 5-6 kilometer information. So what's the point of running all this high resolution grid then? So this is over smoothing, and just probably those models employ very strong dampers, some filters, and some other techniques to smooth solution to remove this 2 delta X and 4 delta waves, and they overdo it. And as a result, the solution don't look like, say, clouds. They look like some blobs, not this kind of nice fluffy clouds that you want. So that's a danger. But that's one of the remedies. So you need to suppress or filter them, but just right amount. And how you do it? Well, you can use direct filter, direct FFT, Fourier analysis, Fourier filtering. You just decompose it into harmonics and reduce amplitude of shortest harmonics like 2 delta X, 4 delta X, and then do a reverse do analysis, synthesis instead of Fourier synthesis, and you effectively suppress some of those waves. But this is expensive, of course, because you involved even with fast Fourier transformation to do it on each every 10th step. Another way to suppress is use a smooth solution with some diffusion process, some artificial diffusion. And that would be more selective. You can control it by changing your diffusion coefficient until you get satisfactory results. So those two, this is concerning suppressing of those, directly suppressing them. Another way of addressing this problem of nonlinear instability, which is actually much more that I prefer, because I don't want to introduce this artificial diffusion and smooth my clouds too much, is actually starve instability, starve it of energy supply. So if you conserve total energy in your scheme, and we're going to talk about in one of next lectures, if you conserve total energy, then there is not enough energy for instability to grow. It's basically you starve instability from energy. If you have just finite amount of energy, even if you start growing in 4 delta X waves, very soon they will run out of juice because not enough energy for them. They will suck energy from all these waves around, and that's it. No, until this energy is populated, again, replenished, there is no more energy to feed the instability. And while it's waiting for more energy to come, actually interaction with other waves will remove energy from 4 and 2 delta X waves themselves towards longer wavelengths. So this is basically one of the best methods to fighting nonlinear instability, is to conserve energy, total energy in the system. And in addition, you have this added benefit. You have more realistic and physically based solution, because conservation of energy is one of those fundamental physical properties of the system that you're trying to simulate. So that's added benefit. So use energy conserving scheme. So that's, of course, it's easier said than done, and we will talk about how we actually do that. Third one is use spectral method. Spectral method, not finite difference. And we're going to talk about that in some of the next lectures. In that case, you can remove m plus k that not represented explicitly, because spectral methods basically create these pairs m plus k, and you just don't create pairs that produce waves that may alias back to the grid. You just get rid of those interactions. So you, in spectral methods, you add actually these things, m plus k, you do it explicitly. So using spectral method, you can avoid it altogether directly. So no smoothing will be required, anything like that. You just don't produce those waves to begin with. But this method is expensive, and recently, although it's been very popular method for solving global equations on sphere spectral methods, but recently it kind of came out of favor because of some problems with utilizing massively parallel computers with this method. And for use dissipative schemes. Use schemes with numerical diffusion in them. Use finite difference schemes with implicit diffusion. So remember, if we use upstream bias scheme, for example, it's very numerically diffusive, and it tends to reduce amplitudes. So it's probably too much. It doesn't. It's too dissipative, too diffusive. But you could use a third order upstream bias scheme. We didn't consider here, but if you just use a pattern instead of 2 grid points, you use, let's say, 3 grid points, it's third order upstream bias scheme. It will be dissipative, but not as much as your upstream bias scheme, first order upstream bias scheme. So it will provide some artificial implicit diffusion that will actually naturally remove or control 2 delta x and 4 delta x waves. So that's approach that plausible, but and it's actually sometimes the only way. Like if you have very strong generation of 2 delta x, so let's say you do a simulation of flow around buildings. So you have this building with very sharp edges, and it just naturally flow regardless of if you conserve energy or not. It generates a lot of 2 and 4 delta x waves because the forcing due to buildings happens in very short scales. So you just create lots of noise at the short scales in that case. And so if you use this kind of dissipative diffusive schemes, then the short waves not allowed to interact much and produce instability because they just naturally remove energy from those small scales. Let's demonstrate one kind of explicit way of smoothing the solution using just second order diffusion. So basically what you do, you add to the right hand side of your equations, let's say you have some equation, and you add here you have advection, your Coriolis force, let's say, or some other sources and things. And then to the right hand side you add this artificial diffusive term, like that. And so you approximate it as our second order representation of second derivative, as you may remember. So here you have so this is in some point k. So you have phi k plus 1 minus 2 phi k plus phi k minus 1 divided by delta x squared. And now if you consider your solution as a linear solution like phi as a function of time times e, I, k, and m delta x. So your x equals to m delta x, so just your grid as we've done before when we consider stability and other things. So if you substitute and do some math, you will get the following equation, that this amplitude dt equals to minus amplitude divided by tau, where tau is, so this one looks like decay equation, remember? It's exponential decay with time scale tau, and this time scale tau apparently it equals to delta x squared divided by 4 nu sine square m delta x divided by 2. So that tau minus 1, so 1 over tau equals to just 4 nu sine square m delta x divided by 2 divided by delta x square. So if you plot it, let's plot it, I don't know, here. So let's plot this response function. So here we have m delta x. So we have here 2 delta x waves. Here we have 4 delta x waves, and so on. And here we have our amplitude, so 1, this dimensionless amplitude. So if you plot this sine square m delta x over 2, we see that m delta x, so it's going to be the following. So this guy is going to be, it will look something like that. So this largest value is 1, and for 4 delta x waves it's going to be 0.5. So it means that biggest response is going to be for 2 delta x waves. They're going to be removed the most, and then about half the rate 4 delta x waves will be also removed. So basically that's what, and other waves is going to be very quickly decay, it's not going to be much. So diffusion basically acts more strongly on 4 and 2 delta x, and some, of course, some other waves, but not as much as these ones. So those guys are like, for example, 8 delta x waves will be removed at 0.14. Only 14% will be removed in one time step, and but I mean those guys will be removed very efficiently. So this one is 14% of 2 delta x waves, so much slower. Of course, from that you get, and of course now it depends on nu. So then you need to multiply to find actual tau. You need to so this is what we plotted, is just 4 sine squared delta x squared. So you need to multiply by nu is to get actual tau. If you want like tau, say for stability reasons, you need to choose tau, and then from that you can compute your nu. So you can try many various nus. You can tune your model such that your solution is not over smooth, by this application of this kind of explicit diffusion scheme. Sometimes people also use that's a separate topic on the whole separate topic on filtering of noise. People use so-called hyperviscosity. So hyperviscosity, which is like fourth order, it's not physical viscosity, because physical viscosity is second order. It's hyperviscosity. It's when you use fourth order derivatives, or even sixth order derivatives. And with each, why you need a higher order? Because then actually the response function is more peaked around 4 and 2 delta x waves, and affects less longer waves. That's what you want. You don't want your artificial smoothing or diffusion procedure affect your actual solution on some beyond certain scale. So the higher derivative you use, the more selective your procedure is toward the shortest waves. And because the second order diffusion is a little bit too much, even 14% for 8 delta X waves is a little bit big number. So it may over smooth your solution. And this one, fourth order hyperviscosity or sixth order hyperviscosity will be much more selective, which is maybe very important for if your resolution is relatively coarse to begin with. So that's, I think, enough. All I wanted to say about nonlinear instability. See you next time.